All right, let's get started with Chapter 3. And Chapter 3 is all about graphing and systems of equations. So we'll start by graphing systems of equations. So just a quick overview of what we're going to learn. We're going to solve a system by graphing. Some vocab for us: systems of equations, independent, inconsistent, and dependent systems. Those are three different types of systems. And then a linear system is just a bunch of lines. So system is more than one, linear is line. Something like that is going to be a linear system. We're going to try to figure out where two lines, sometimes more than two lines, but usually just two lines, where they cross. That's what we're going to try to solve in this section. Okay, so just a quick review. You need to know how to graph straight lines. So go ahead and graph those equations for me, please. And then use one coordinate plane for all three on 4, 5, and 6. You should have 3 lines on a single coordinate plane for 4, 5, and 6. Pause the video, try those graphs. Okay, let's get into this. A system of equations is a set of 2 or more equations that use the same variables. If the graph of each equation in the system of 2 variables is a line, then we're talking about a linear system. We use the bracket to organize the equations and say that we're working with them together. Notice that both equations have y's and x's. So the solution of a system is the set of values for the variables that makes all the equations true. So what x and y makes this equation true and this equation true? And that's what we're going to try to figure out. And the place where that happens is where the lines intersect, where they cross each other. So we're going to be graphing here. So let's graph these together. So why don't we do this with some slope-intercept. In the first equation, I'm going to move the x over, minus 7, and then we'll divide by 2. So y equals negative 1/2 x minus 7 over 2, which is 3.5. Let's go ahead and graph this. So I'm going to go down to 3.5. 1, 2, 3.5. We'll make a dot. And then we're going to go down 1 and over 2. Down 1 over 2. And we'll connect our lines. I could go another down 1 over 2. Why'd you go away? Come back. And we could go up 1 and over 2 in the other direction and connect all our lines like that. And how about this other one? 2x minus 3y equals 0. Let's get y by itself. We'll move it to the other side. And we'll divide by 3. And so we'll have 2/3 x equals y. Intersection at 0. We're going to go up 2 and over 3. Same thing as going down 2 and over 3. And we can see here, it looks like we're going to cross, if I continued that line out, right here at, this looks like negative 3, comma, negative 2. Let's plug this in and make sure that this works. We'll plug it into the first equation first. So x was negative 3 plus 2 times the y value. The y is negative 2. So negative 3 minus 4, that's negative 7, and that's what it's supposed to equal. So that one works. Let's check for the second equation. 2x, so 2 times negative 3, minus 3y. See what we get here. This is negative 6, and this is plus 6, and so we get 0, and that's what we're supposed to get. So this is our answer, negative 3, negative 2. All right, so see if you can do that yourself. Solve for that system of equations. 2 equations, find where they cross. Okay, so for this one, we're going to use Desmos. So we've got a table of data here. And so in here, we've got all of the winning times for the Olympic 400-meter dash over the last, from 2000 all the way back to 1968. All right, so we're going to make a model out of this. We're going to use Desmos and see what happens. So I've gone over to Desmos. And I've already punched those numbers in. So here's the table. Now notice here, we haven't done this yet in Desmos. I've got 2 y values. If I go back in here, get this out of the way. So year is going to be the x value. And we're going to make 1968 year 0, the starting point. You are driving me crazy. Go away. There we go. All right, so year 0, this is 1968. In 1968, Min ran the 400 meters in 43.86 seconds. and the women ran it in 5203. We've got that in here. Okay. To get this, all I did is I moved over, clicked, and typed Y2. If I wanted a Y3, I could go in here and type Y3 and then put it in there. Don't want that. I'm going to get rid of it. All right, so type in your table, pause the video if you need to, and type that table into Desmos. Okay, so now that we have this, we want to see the line of best fit that goes through these. So just a reminder, here's how we do line of best fit. Y equals mx plus b. Y1, use the squiggle, equals mx1 plus b. And it's going to create the line of best fit, the line that best fits these dots for the first line here. This was the men. We also want one for the women, so we're going to do the same thing, but this time the women are in Y2. We're still using the same years, so years were still x1 plus some b. We've got our line that goes through that. Pause the video, type in those two equations, make sure you get this. All right, so in 1968, the men were much faster than the women, but as we go on in time here, the women are catching up, and we're closing the gap, closing the gap, closing the gap. Let's find out when they're going to be running at the same speed if these trends continue. Okay, now we could argue whether these trends would continue or not, but if we're assuming that they are, when are these lines going to cross? What's the solution of the system of equations? So let's move Desmos over and just keep dragging until we see where they cross. Now the nice thing about Desmos is when they cross, if I just click on it, it will find the point. If I click just off of it, it won't stick. But if I click on the intersection, it will stick and give me the point. So 99.72, that's the x value. That's how many years, remember, from our starting point from 1968. So if we round it up, 100 years after 1968 would be 2068. So in 2068, both the men and the women are going to run 42.002 seconds if these trends continue. All right, use that information to answer 2A and B. Okay, wrapping up, the last thing here is we need to know about some different types of systems. So if our lines cross, we're going to call this an independent solution, an independent system, because it has one solution. But what if we have two lines that are lying on top of each other? These are dependent on each other. There are no unique solutions because there's lots of places that lie on both lines if the lines are on top of each other. And then we have our parallel lines. Parallel lines, there's no solution, and we call them inconsistent systems. So how can we tell which one's which? Just by looking at them without even having to graph. So here's what we're going to do. If we line these up, so the top equation is y equals 2x plus 3. Let's move the bottom equation over so we get y equals. If I added that 2x, I'd also get 2x but plus 1. All right, if the x's and the y's match up perfectly, but C does not, these are going to be parallel lines. They have the same slope, but they cross the y-axis at a different intercept. These are going to be parallel. Remember, parallel lines here are inconsistent. So this one we would say right away is inconsistent. Now, if the two equations are exactly the same, so if this was a 3 to start with, we would say that they're the same line. So we're going to call those dependent. And if in any case either the y's or the x's, like 1x versus 2x's, if at any time they weren't the same, then we're going to say it's an independent solution. Okay? Now, the one exception to that is if they're multiples of each other. Sorry, going the wrong way. If this was my equation, y equals 2x plus 3, and my next one is 2y equals 4x plus 6, if I times this equation, the top one, by 2, then they are the same equation, and so they'd be dependent. Okay? Otherwise, if the x's and the y's don't match up, they're independent. All right, try those, 3A, B, and C, and your job here is done. We'll see you in class next time. Good luck with those.